Hello and welcome students to Make Pro classes, my official YouTube channel. Myself Biraj Mojumdar, and I am continuing manufacturing processes, and we have completed our module 1 and move on to module 2, and in module 2 we have also completed 8 lectures, and in the previous lectures I have covered introduction to bulk metal and sheet metal forming process, then plastic deformation as well as yield criteria, and fundamentals of hot and cold working processes. And in the last video lecture I have also completed the sheet forming operations. Okay, now today we will move on to different bulk forming processes, as I previously covered the extrusion process as well, and today we will be moving on to rolling process. So let us start the video. Hello students, welcome to today's class of rolling, and you already heard about the rolling operation. This is also one of the most widely used bulk forming operation, and in rolling process we are actually reducing the size or diameter, you can say, of a particular metal material. So today we will be having this discussion on rolling. Now rolling is a process of plastically deforming metal by passing it between rolls. Most widely used, as I earlier told you, and it has got high production as well as close tolerance. Next, the friction between the rolls and the metal surface produces high compressive stress as well. Now it is also a hot working process unless mentioned as cold working or cold rolling, and here metal will undergo biaxial compression. As I earlier told you, these things are going to be very important, so you must take a note of this, that metal will undergo biaxial compression in rolling process. So from this slide you can easily conclude that rolling is a very economical process for producing large volume of material with constant cross section, and rolling is also a process where the metal is compressed between two rotating mills for reducing its cross-sectional area. So in this particular picture you can see over here that a strip or plate is being passed through two rotating mills which are moving in opposite direction to each other, and the strip or plate is being compressed, and the size of the strip or plate is being reduced, or you can say the cross-section of the particular plate is being reduced. So this is a typical rolling process you can see over here. It is one of the most widely used of all the metalworking process because of its high productivity and very low cost. Rolling would be able to produce components having constant cross section throughout its length. Many shapes such as I section, you can say T section, L section. Okay, so I can show you a picture. So these are the pictures. These are the products, generally rolled products, that you can make out of rolling process. So you can see over here I section, okay, then T section, L section you can see over here. This is the T section, and channel sections are possible, you can see over here, but not very complex shapes. Now it is also possible to produce special sections such as railway wagon wheels by rolling individual pieces. So here you can see rolling is a very versatile process in metal forming process, and it's being widely being used due to its cheap, low cost and high productivity and various channel sections, and it is being widely used in railway wagon wheels as well. Okay, so rolling is normally a hot, working process unless specified mentioned as cold rolling. So in this picture there are different sections are being rolled. So you can see over here these are the ingots. Then ingots are being compressed, here you can see over here, and being drawn into wires or bars or seamless pipes as well. Okay, So these are the different applications of rolling process. And from this is the billet and this is the bloom. As I earlier discussed with you, the difference between the ingots, billets and blooms as well. Now from bloom we are getting the this eye section you can see over here. This is the structural shapes, this is the rails, okay. And from billet we are getting this tube rounds, okay, and from that we are getting seamless tubes, then cold drawn bars, wires, etc. And from slab you are getting this hot strip, cold strip, okay, seats, welded pipes, plates, steel plates as well, okay. So these are the different applications portions of rolling process. Now as I earlier mentioned you that rolling is normally a hot working process unless specifically mentioned as cold rolling, and it is done, as you already can guess, hot rolling. For hot rolling we have to perform the operation above the recrystallization temperature as well, and it results in fine grain structure, okay. And then we have got good surface quality and final dimensions are somewhat less accurate. And breakdown of ingots into blooms and billets is done by hot rolling only. This is followed by further hot rolling into plate, sheet, rod, bar, pipe, rail. As you can see in the previous slide, we have discussed the application portions. Now hot rolling is terminated when the temperature falls about 50 to 100 degrees Celsius above the recrystallization temperature, okay. So the metal is taken into rolls by friction and subsequently compressed to obtain the final shape. And the thickness of the metal that can be drawn into rolls depend on the roughness of the roll surface. Rougher rolls would be able to achieve greater reduction than the smoother rolls. But the roll surface gets embedded into the rolled metal, thus producing rough surface. And I will discuss in later part the angle of bite as well, the different nomenclatures of the this particular hot rolling process. One more thing I would like to share with you, that the volume of the metal that enters the rolling stand should be same as that leaving it, except in initial process where there might be some loss due to filling of voids and cavities in the ingots. Now, since the area of the cross section gets decreased, the metal leaving the rolls would be at higher velocity than when it entered. So you can conclude from the particular rolling process here only. Here you can see since the area of the cross section, you can see over here, the area of the cross section is reduced or get decreased, the metal leaving the rolls here, the velocity, so the velocity will be this velocity, say velocity of exit, this is the velocity of entry. So velocity of exit will always be greater than the velocity of entry. So you can say the metal leaving the rolls would be at higher velocity than when it entered. So initially when the metal enters the rolls, the surface speed of rolls is higher than that of the incoming metal, whereas the metal velocity at the exit is higher than that of the surface speed of the rolls. And between the entry and exit, the velocity of the metal is continuously changing, whereas the roll velocity remains same. So this roll velocity, say VR, it remains constant, but the velocity of the particular this stripe keeps on changing, okay. Somewhere in the contact length, actually the velocities of the metal and rolls are same, which is designated as neutral plane. So I can write it for you, this is very important. So somewhere in between this shape there will be a place which will be known as neutral plane, when the roll velocity will be equal to your the velocity of metal, you can say velocity of metal, okay. So that particular place is known as neutral plane, okay. So where the metal velocities of the metal and roll are same is known as the neutral plane, okay. Now the pressure on rolls gradually builds up from the entry to the neutral point where it is highest, So pressure at neutral plane, pressure would be highest at the neutral plane, and then decreases it somewhere, say here we are getting the neutral plane and the pressure is highest here, okay, and then it decreases, then as it moves away from the neutral plane the pressure decreases, okay, till it reaches the exit. So the roll separating force which separates the two rolls apart can be obtained by multiplying the average roll pressure. So you have to take average roll pressure, so P average, as because we are having maximum and minimum values, so we have to obtain the average value of the pressure, now which is a function of contact length, that is a contact length. Now the average roll pressure can be decreased by reducing the maximum pressure, which is a function of contact length, okay. So smaller contact length means the less friction acting on the roll. Thus by reducing the contact length it is possible to decrease roll separating force, okay. So if you decrease the pressure, the roll separating force will also decrease, okay, and which in turn can be achieved by reducing the roll diameter also. So roll diameter, this is the roll diameter, this is the roll diameter. So by reducing the contact length, as you can see, it is possible to decrease the roll separating force, and in turn can be achieved by reducing the roll diameter as well, since smaller rolls would have less contact length and than larger rolls for the same reduction. So the smaller rolls are used for larger reductions and cold rolling where roll separating forces are large, and the smaller rolls would not have enough rigidity to support a large roll separating force. Hence backup rolls, say in the later slides we'll see backup rolls are being used here, say this one. So you can see these are the backup rolls, okay. So backup rolls are attached to the small rolls to provide the necessary rigidity. Now though higher friction between rolls and metal is required for increasing the reduction achieved, it also increases the roll separating forces as well, okay. So next let us move on to next slide. Now we will discuss the change in grains structure in hot rolling. So you can see from here in this particular picture, this is the entry point and this is the exit point, and these are the rollers you can see over here. So in the entry you can see over here the grain structure looks like somewhat this one, okay. Now after being compressed or rolled, the grain structures changes. So you can easily see the difference in the grain structures. So it says wrought product with large grains. So these are the large grains, and new grains are forming after it being rolled, okay. Now here it is the recrystallization temperature is complete. So this is the wrought product with smaller uniform grain structure. So here you can see the elongated grains. So this is the deformed elongated grains. Now hot rolling is an effective way to reduce grain size in metals for improved strength and ductility. So it is very effective process to increase the strength and ductility as well. Now coming to the roll bending process. It is a continuous form of 3-point bending in roll bending, where plates, sheets, rolls shapes can be bent to a desired curvature on forming rolls. Upper roll being adjustable to control the degree of curvature. So you can see over here, this one is a roll bending, roll forming process. I sections are being produced out of this operation. So you can see previously it was somewhat like the billet or bloom, you can say. Next it was compressed and gradually it took the shape of somewhat the T section, okay. So this is the operation known as roll forming process. I have already discussed with you the different shapes that can be rolled, that can be formed out of the rolling process. As you can see over here, there are different shapes, T, L, I sections as well. Okay. Next, let us discuss on sheet rolling process. In sheet rolling, we are only attempting to reduce the cross section thickness of a material. So you can see over here, this sheet rolling, the sheets are being rolled and it is being coiled in this particular diagram. You can see over here, this is the rolled strips. Next is your ring rolling. So you can see there are different forms of rolling operation. Ring rolls are used for tube rolling, ring rolling, etc. As the rolls squeeze and rotate, the wall thickness is reduced and the diameter of the ring increases. Shaped rolls can be used to produce a wide variety of cross-section profiles. Ring rolls are made of spheroidized graphite, bainitic, and pearlitic matrix or alloy cast steel base. So here you will find this is a rolling process, ring rolling actually. So here we are having the rounding roll. This is the ideal roll. This is actually guides the whole process. You can say this particular job also. This is the edging roll. It also helps in guiding the workpiece as well. And this is the main roll. Power is coming from this particular main roll. Okay. Now cross-sectional view you can see over here, and the final product, the practical, the actual product you can see over here. So this is the process. Now, as I earlier discussed with you, elongated to grain size after the rolling process. You can see over here, deforming and reducing the grain size. Okay. So next, coming to the cold rolling process, it is done below the recrystallization temperature. Products are sheet, strip, foil, etc. with good surface finish and increased mechanical strength. As I earlier told you that strength and ductility increases in rolling process, and as because it is cold rolling process, so it will have closed product dimensions as well. Now it is performed on 4 high or cluster type rolling mills due to high force and power. Now thread rolling, it is also one of the most versatile and most widely being used process for making threads. Okay, so it is used to produce threads in substantial quantities. This is a cold forming process in which the threads are formed by rolling a thread blank between hardened dies that cause the metal to flow radially into the desired shape. No metal is removed. Greater strength, smoother, harder, and more wear resistant surface than cut threads. Now measured diameter is always greater than the diameter of the blank. Blank diameter is little larger, that is around 0.002 inch than the pitch diameter of the thread, and it is restricted mainly to ductile materials. Okay. So here you will find the threading operation. This is the thread rolling. So this you can see, these are the threads that will be imprinted on this particular moving workpiece. Okay. So this is the collet you can see over here. Now this is the blank, this is a moving die, this is a stationary die, and these are the threaded parts for both. This one you can see over here. Okay, so these particular threads are being imprinted on the blank. Okay. Now pack rolling. Pack rolling involves hot rolling multiple sheets of materials at once, such as aluminum foil. Okay, and it is used for improved productivity. It is used for also making aluminum foils that are being widely used by restaurants, packaging industries as well. And you can see over here, matte satin side foil to foil contact, shiny blind side foil to foil contact due to high contact stresses with polished rolls. A thin surface oxide film prevents their welding. So here you will find the package rolling. This is the machine, and this is the strip, and these are the rollers you can see over here. Now this is the arrangement of rolls in a rolling mill, also known as the rolling stand, and it depends, varies depending upon the application only. Okay, and this one, the first one you can see over here, this is known as too high non-reversing rolling stand arrangement is the most common. This is the most common arrangement. In this, the rolls always move in only one direction, this direction. And in this one, high reversing rolling stand where the direction of roll rotation can be reversed. Here you can see over here. And this type of stand is particularly useful in reducing the handling of the hot metal in between the rolling passes. You can see over here. When all the metal has reached the right side, the direction of the rolls is reversed and the metal is allowed to enter into the next pass. These stands are more expensive compared to the non-reversible type because of the reversible drive needed. So here you need the reversible drive. Okay. Next, actually this was the reversible drive. Sorry for my mistake. And this is the actually three high rolling arrangement actually. So it is used for rolling of two continuous passes in a rolling sequence without reversing the drives. Okay. Rolling stand arrangement is the most common arrangement. Okay. In this particular arrangement, the rolls always move in only one direction. So you can see over here this direction only. And in this particular diagram, you can see over here it is a too high, reversing rolling stand. What is the difference? The difference is that the direction of the roll can be reversed, and this type of stand is particularly useful in reducing the handling of the hot metal in between the rolling passes. When the metal has reached the right side of the particular this rolling operation, the direction of the rolls is reversed and the metal is allowed to enter into the next pass. So you can see over here, these stands are more expensive compared to the non-reversible type because of the reversible drive needed. Now coming to the next diagram, you can see over here, it is a three high rolling mill and it is used for rolling of two continuous passes. You can see over here in a rolling sequence without reversing the drives. And after all the metal has passed through the bottom roll set, the end of the metal is entered into the other set of the roll for the next pass. For this purpose, a table tilting arrangement is required to bring the metal to the level with the rolls. So next, here you can see a 4 high rolling mill stand. Okay, it is used essentially for a 2 high rolling mill, but with the small sized rolls. This one's small sized rolls. The other two rolls are the backup rolls. These are the backup. These are the backup rolls actually. The bigger ones are the backup rolls for providing the necessary rigidity to the small rolls. This one. Okay. A better backup can be provided to the small rolls with a cluster of arrangement. So you can see over here. This is the cluster of arrangement over here. So these big rolls are known as the backup rolls. Okay. And for the rolling arrangements requiring large reduction, a number of free rotating wheels instead of single small roll are fixed to a large backup roll in the planetary rolling mill. Okay. Now this is the roll piercing operation. So you can see over here, tensile stresses are being acted on this particular void initiation, and this is the cavity. And you can see over here, this is the tube, this one, and this is the mandrel. Okay, so you can see these are the two rolls. Now it is a variation of rolling called roll piercing. The billet or round stock is rolled between two rolls, both of them rotating in the same direction with their axis at an angle of 4.5 to 6.5 degree. And these rolls have a central cylindrical portion with the sides tapering slightly, and there are two small side rolls which help in guiding the metal. Because of the angle at which the roll meets the metal actually, it gets in addition to a rotary motion and additional axial advances which brings the metal into the rolls. This cross rolling action makes the metal friable at the center, which is then easily pierced and given a cylindrical shape by the center piercing mandrel. Now manufacture of gears by rolling operation. The straight and the helical teeth of disc or rod type external steel gears of small to medium diameter and module are generated by cold rolling, and it is producing high accuracy and surface integrity as well, and it is employed for high productivity and high quality. This is a costly machine, you can over here, and it is used for large size gears, and it is formed by hot rolling and then finished by machining. So here you can see these are the gear rolls. The work or blank is being placed in between of them. So this is a gear rolling between 3 gear roll tools. Now coming to the lubrication portion for rolling. Lubrication is one of the vital operation being used during rolling process. So hot rolling of ferrous metals is done without a lubricant, but as because ferrous are more prone to rust. For a hot rolling of non-ferrous metals, a wide variety of compounded oils, emulsions, and fatty acids are used. Cold rolling lubricants are water-soluble oils, low-viscosity lubricants such as the mineral oils, emulsions, paraffin, and fatty acids. Now, camber. So you can see over here, production of camber. Look, the use of cambered rolls to compensate for roll bending. So we are using camber rolls for compensate the roll bending. Somewhat, what happens? There may be a variation in the thickness. Okay, we generally obtain uniform cross section, but if you don't provide cambered to the rolls, it will produce a variation in the cross section. As you can see over here, without camber, the rolled metal is being of non-uniform cross section. So it says the use of cambered rolls to compensate for roll bending, this one, and uncambered rolls gives variation of thickness, this one. Okay, so camber can be used to correct the roll deflection. Okay, now planetary mill, this is very important. It consists of a pair of heavy backing rolls surrounded by a large number of planetary rolls. Each planetary roll gives an almost constant reduction to the slab as it sweeps out a circular path between the backing rolls and the slab. As each pair of planetary rolls ceases to have contact with the workpiece, another pair of rolls may contact with and repeat that particular reduction. The overall reduction is the summation of a series of small reductions by each pair of rolls. Therefore, the planetary mill can reduce a slab directly to strip in one pass through the mill. The operation requires feed rolls to introduce the slab into the mill and a pair of finishing rolls on the exit to improve the surface finish. So this is the arrangement of a planetary rolls, as you can see over here. Okay, now look, for the rolling arrangements requiring a large reduction, a number of free rotating wheels. Okay, this working roll being idle, as you can see over here. Instead of small, the rolling arrangements requiring large reduction, we are using a number of free rotating wheels instead of a single small roll, and are fixed to a large backup roll, this one, and these are all the idle rolls. So you can see over here this working roll. It is a planetary rolling mill arrangement, and since the final shape required cannot be obtained in a single pass, the rolling mills are generally arranged with rolls which have more than one pass machined into them, so that the material coming out of one pass is then to be fed back to the other pass by reversing the roll direction by arranging the rolling mills in a tandem. So it is general practice to maintain tension in the strip between the strands in the interest of keeping it flat, and also to control the thickness closely. This also helps in reducing the roll separating force as well. Now the steel coming out of a blast furnace or a remelting shop is in the form of an ingot, which is a cross section of the order of, as I earlier told you that. So I will just write it for you. It will be having a cross section of 600 into 600. Okay, millimeter. That will be the cross section of an ingot of a steel coming out of remelting or blast furnace. Okay, now these ingots are further processed in rolling mills to produce the intermediate shapes such as blooms. And slabs and billets. Okay. Now, blooms are generally square cross section, as I earlier told you in the previous classes, and with cross sections varying from particular for blooms, it is around 150 into 150, as it is a square cross section, to 400 into 400 millimeter. So that is the range for the cross section of the blooms. Okay, now the slabs, coming to the slabs. Slabs are a rectangular cross section with widths varying from 500 to 1800 millimeter. 1800 millimeter. Okay, and thickness varies from 50 to 300. 50 to 300 you can write for slabs. Okay, now billets. The next one is the billets. For billets, we are having again rectangular cross sections with size varying from 40 into 40 millimeter to 150 into 150 millimeter. So you can see, so this is the most reduced shapes. Okay, now the ingot obtained by casting would normally have defects such as the shrinkage cavities, blowholes, and slag inclusions. Now, when the ingot is rolled, the shrinkage cavity, called as the pipe, is towards the end, which is then cropped after a few initial passes to reduce the defects in the finished product. So the blooming and the slabbing mills which produce blooms and slabs from the ingots are generally the reversible two high rolling stands. What happens after the roll being passed from one in single pass, it is being again pushed into second pass. That's why we are using two high rolling stands. And after passing through the second pass, maximum of the defects are being reduced. The metal is turned 90 degrees in the initial phases to enable the material to be uniformly compressed from all sides, so that any of the internal voids such as blowholes are eliminated and the sag inclusions are segregated. The rolls are generally manufactured of chilled cast iron, carbon steel, and alloy steels. So you must take note, the rolls are generally manufactured of chilled cast iron, carbon steel, and alloy steels. The soft rolls having a hardness of 150 to 250 BHN are used in roughing stands of the heavy section mills and billet mills. The semi-hard rolls are having 250 to 400 BHN and are used in roughing stands of rail structure mills and finishing stands of heavy section mills and billet mills also. Hard rolls are having 400 to 600 BHN and are used to make finishing stands of sheets, railway structure, and backing rolls for smaller diameter rolls. They may sometimes have a roll surface of hard alloy such as tungsten carbide. The extra hard rolls with 600 to 800 BHN are used for border rolling. The smaller rolls in this category may be made of hard materials like tungsten carbide. Now, coming to this particular geometry of rolling process. So, here you can see over here, H1 was the initial thickness, HF was the final. So, H0 minus HF will give you the reduced or the reduction in the diameter. Okay. Now, here is the alpha, that is a bite angle, you can see over here. Okay, so previously the width V0, now it is V1, as you can see over here. Now, neutral plane, they have seen over here, this is the neutral plane. Now, this is the lagging zone and this is the leading zone. So, this is the geometry of the rolling process. Now, draft, that is a total reduction or draft, as I earlier told you, is equal to H0 minus HF, and it is also given by in terms of bite angle and radius of the rolling mills as 2 into R minus R cos alpha, and it is also can be written as D into 1 minus cos alpha. Usually the reduction in blooming mills is about 100 millimeter in slabbing mills, about 50 to 60 millimeter. Now maximum draft possible is given by mu is the coefficient of friction between the rolling surface and the plate or strip or workpiece, you can say, and the value of the maximum draft is mu square into r. R is the radius of the diameter, radius of the mills, the rolling mills. Okay. For unaided entry, mu should always be greater than equal to tan alpha. Alpha means the bite angle. Okay. Now, type of rolling and maximum generally angle of bite we are going to use are for cold rolling with lubrication and smooth roll surfaces. The bite angle have a range of 3 to 4 degree, and for hot rolling of tubes, it is a larger one, about 12 to 14. For hot rolling of sheets, it is even larger, 15 to 22, and highest bite angle is used for hot rolling with rough mill rolls, that is the separation of rolls, and the bite angle varies from 27 to 34. Next, roll strip contact length. So this is the H0, this is the HF final height, you can see over here. This is the alpha, this is the bite angle, you can see, and R is the roll radius, P is the roll pressure, and this is the roll, this is the contact length, you can see over here. Okay. Now this V0 is the this speed of this particular workpiece, you can see over here, or strip, you can say, and VR is the rolling mill velocity. Now the formula for roll strip contact length is given as L equal to R into alpha. So this one L will be R will be the radius, this one, into alpha is the bite angle, and alpha should always be in radian. Okay, so this is very important formula for solving of numerical purpose. So you can take note over here, that is L equal to R into alpha. Next we have the defects are in rolling are surface defects. It is as production of scale, rust, scratches, pits and cracks on the surfaces, and it is generally caused by the inclusions and impurities in the materials. Next is your wavy edges, and it is due to the strip is thinner along its edges than it's at its center, and it is caused due to roll bending edges elongates more and buckles. Next is very important, alligatoring. What happens, edge generally breaks in the exit of the particular strips or rolls, and it is caused by non-uniform deformation. Okay, so again I have short it out. These are very important. You must take a note or take a screenshot of this particular defects. So surface defects comes as laps, scaps, seams, silvers. Then you are having structural defects. The structural defects, I have given you a picture. This is the structural defect, you can see over here. So this is the deformed roll, and resultant shape of the output you can see over here, due to non-uniformity of the reduction. This is the incoming material, you can see over here. So deformation of roll surface due to the bending of rolls under rolling pressure, as you can see over here. Okay. Next, your wavy edges, as I earlier discussed with you. Next is edge cracks, alligatoring. This is a clear picture for you. So you can see over here, due to non-uniformity, the roll strips separates or breaks down. Okay. So these are the rolling defects, as you can see over here. And that's all for rolling process. Hope you have enjoyed today's session of metal forming. Thank you for watching.